When you first learn to multiply polynomials, you're taught the FOIL method: first, outer, inner, last. It's a reliable way to crunch two binomials together. FOIL functions as a memorization trick, a rigid set of instructions that obscures the underlying mathematical architecture of the expansion. Try to use it on anything larger, like a trinomial, and the four-step acronym immediately breaks down. To see the real mechanics, let's define an arbitrary polynomial p of x with a degree of n. Next to it, we place a second polynomial, q of x, with degree m. These could have degrees in the hundreds. At that scale, manual distribution lines are impossible to track. We require a mathematically rigorous, generalized framework to handle this expansion. This system must allow us to target any specific term in our final answer, x to the k, and determine its exact coefficient without calculating the surrounding math. Building that requires a shift in perspective. We must look away from the variables and focus entirely on the indices of the coefficients. Advancing in mathematics requires building universal models that can be translated into programmable code, removing the need for manual calculation entirely. We can hunt for the underlying pattern by looking at a quadratic polynomial multiplied by a linear polynomial. Executing a standard term-by-term multiplication fills our grid with every possible combination. If we reorganize these terms by their exponents, we can see how they were constructed. Isolate the x cubed term on the screen. This term was generated by multiplying the coefficients a2 and b1. Look at the subscript indices of those coefficients. 2 plus 1 equals 3, matching the exponent of the term. We see the same result with the x squared term, which is composed of two combined cross terms, a1b1 and a2b0. The indices follow the same logic. 1 plus 1 is 2. 2 plus 0 is also 2. To find the coefficient of any exponent k, the subscript indices of the multiplying terms must sum exactly to k. This algebraic expansion operates as a strictly regulated mechanical tracking system that is dictated by the fundamental laws of exponents. We can now translate this index pattern into formal summation notation, the discrete convolution sum. Within this summation, j serves as the running index counter. This is paired with the complement index, k minus j. This specific arrangement ensures that the two indices will always sum to our target exponent, k. We can test this formula using two quadratic polynomials. First, we extract their integer coefficients and place them in a data ledger. To execute this as a programmable algorithm, we have to handle queries for indices that don't exist in our inputs, like a3 or b4. We solve this boundary problem using zero padding. We add rows to our ledger, explicitly declaring that any index exceeding the polynomial's original degree is equal to 0. Combining the index summation rule with zero padding allows a computer to multiply polynomials without needing human intuition or visual distribution lines. We initiate the loop for the constant term, where k equals 0. The formula grabs a0 and b0, logging a result of 1. Moving to k equals 1, the formula pulls the two required pairs, a0b1 and a1b0, resulting in an output of 3. At k equals 2, the algorithm scans 3 distinct pairs from the ledger. The summed output logs as 4. At k equals 3, the formula reaches for coefficient indices that exceed the limits of our original quadratics. Here, the zero padding takes effect. As the algorithm calls for a3b0 and a0b3, they are instantly voided as zeros. The algorithm bypasses these voided terms and sums only the valid inner pairs, logging a result of 3. The final cycle for k equals 4 yields a single valid pair, a2b2, logging our final output of 1. Zero padding acts as a mathematical filter, safely aborting impossible combinations without breaking the continuous computational loop. We gather the outputs from the loop, 1, 3, 4, 3, 1, and map them back to their corresponding exponents to construct the final product. This loop is automated, but we must define exactly when it knows to terminate. The algorithm's bounding limit is the maximum possible exponent. The index k runs from 0 up to a ceiling of m plus n. For our quadratics, with degrees of 2 and 2, the loop correctly terminates at 4. Because this formula always combines real coefficients into a finite set of new terms, the result of polynomial multiplication is guaranteed to be another polynomial. This fundamental behavior is defined as the property of closure. This property distinguishes multiplication from operations like division, which often results in rational functions rather than polynomials. For software implementation, closure means the output of one convolution sum can be fed back into the next operation as a standard input array. By formalizing the convolution sum, we have moved from a manual arithmetic trick to a programmatic algorithm that can handle any degree of n and m using the same core logic.